So when's our homework due?
Wednesday.
Wednesday, okay. And then next week is we have spring break, right? No, we don't have spring break at all, do we? Oh, we have fall break. I think it's next week, isn't it? I haven't checked, but that sounds right. So there won't be, obviously, there won't be any lab on Monday next week because we won't be here. But if you want, I can open up the lab. You can stay in here during that time and think about the lab we would be doing if we weren't having a fall break. But you don't have to. So what I want to do is I just want to do a lot of examples of how you apply F equals MA today. So what we're going to do in the lab today, and it's a very, very systematic thing to do. If you just kind of follow the steps, you really can't make a mistake in any of them. So last time we had the following. We had a table. Right now there's no friction. We're going to relax that probably tomorrow, maybe today. And we had a mass here. That was M1. And we had a pulley. And then we had a mass here, M2. And this pulley was massless and frictionless. Okay, what did we assume about this string? The string is also massless as well. And if I don't, right now until probably November, if I don't say anything in a problem, always make these assumptions that the pulley is always going to be massless and frictionless, and the string is always massless. If I forget to mention that, we're going to make that assumption until November sometime. Then we're going to make it more realistic. And so what we wanted to do is we wanted to find the acceleration of each mass and the tension and the string. So what do we do with these? Always, as soon as you start hearing acceleration and things like tension, force words, what do you think for the rest of your life, meaning as long as you're in this class, the next semester? A free body diagram. And how many free body diagrams are we going to have in this case? Two. And what does a free body diagram do? It's going to be a diagram that shows all the forces on an object. So we're going to start with M1 here. So without looking at your notes, we're trying not to look at your notes. What did we say were all the forces acting on M1? Okay, the weight, how does it always have to go? Down, because weight is caused by what? The gravitational attraction of the Earth on whatever object we have. Okay, so this is the object's weight here, W1. And I stated without proof what that was equal to. What did I state that was equal to?
G.
Almost. Mass times G. Okay, so this is going to be M1 times G. And I stated that without proof. Later on, I'm going to prove that. We'll figure out how to calculate our weight on, if you go to Mars, how much would you weigh on Mars? I'll show you how to calculate that. It's going to be very, very easy to do. Okay, what else is acting on our object? Normal. And what does normal mean?
Mathematical normal, so it's perpendicular.
Yeah, normal mathematically always means perpendicular. And so it's going to be perpendicular to what?
Your surface.
The surface. Because what causes the normal force?
Surface.
A surface. You have to be on a surface. If you touch a surface, you have a normal. So here's your normal. And this normal force, this is really the force table exerts on M1. What else?
Tension
Going?
towards the bowling.
Yeah, can ropes ever go the other way? No, ropes can only pull. Do they ever push? No, they never caught up. Okay. So this is going to be your tension. We're going to call this T1. And what's the next thing you do with all these? You always, for any diagram, you always set up a what? A coordinate system. And make your coordinate system have the same form as the object moves. So which way is this object moving? This way. So I'm going to take just a regular standard coordinate system. So the object's moving this way, so I'm going to take a coordinate system like this. And which way do we always take to be positive? Always take the direction
Yeah.
the object moves to be positive. So in this case here, this is moving to the right, so I'm gonna take this to be positive. Now, what about vertically? Is it moving up or down? So does it matter what we take to be positive? You can take either one. So I think we took up to be positive, right, last time? So we took this. Okay, so now let's do, I'm gonna apply my F net equals MA to this guy. And then we do the other one. What are you gonna do with Newton's second law here? You're always going to break it into components. I'm gonna say your net force, the x direction equals M1 A1x. And the net force in the y direction equals M1 A1y. Now from that free body diagram, okay, when we say net force, what does the net force really mean? It just means the
Forces added.
just all the forces added together. It's just your total or your sum, put in your favorite word. So in this case here, how many forces do we have acting in the x direction? Only one. So if I look here from this free body diagram, the only force acting in the x direction is T. So this has to be T1 equals M1 A1x. Well, look in the y direction. How many forces do we have in the y direction? We have two. We have the normal and we have the weight. So if I were to look at all the forces in the y direction, in other words, the sum of those, what would I have?
And
It's going to add together to be 0. I agree. But just from this side, if you were to just do this guy here, it's going to be what?
minus W1.
Yeah, it's going to have to be n. Why is it n minus W1, not W1 minus n?
It's not supposed
Because going up is positive. Why? Because somebody said it, and that's what I wrote down on Friday. So this is going to be n minus your W1. I should put a little 1 on here because it's a normal force on the first mass. Okay, equals. Now, somebody said that this is 0, and they're right. Why is that 0? Is the object moving in the y direction? No. So therefore, the acceleration in the y direction has to be 0. And this just tells me N1 equals W1. Right now, that's not very interesting. And that makes sense because if these two were different, what would this object do? It'd be moving in the y direction, which it is now. Does that make sense? Okay, that's all we can do with that right now. How many unknowns do we have here?
Two.
Yeah, we don't know A1x and we don't know T1. Okay, so we have two unknowns. And from algebra, when you're a wee little ninth grader, you start learning, or eighth grader, whenever you start learning algebra, how many equations do you need? The same number as the number of unknowns. So we have two unknowns here, so we're going to need at least two equations. So how do we get our second equation?
Free body diagram.
For
That's 2.
mass 2. So now let's do this one. So what are all the forces acting on my body here? Weight going down? And
Tension.
is there normal?
No.
How come?
Tension.
There's no surface. If it was on a surface, then there'd be a normal, but there's no surface. I mean, so there can't be a normal. So we're gonna have then this tension T2. Now, which way is this up? Now we need the coordinate system. Which way is this object moving? Just down. So we're gonna have a standard coordinate system. If it's moving down, then which way do we have to take to be positive? Down. Always take the direction it moves to be positive. So if it's moving down, that becomes impositive. So we're gonna have our net force now equals M2 A2y. We break this into components, like we always will. I'm still on the board there. And I am. Ooh, okay. What did we do with the X force on Friday? Okay, we didn't cancel it, although that's really what we did, but we didn't use a better word. We ignored it because, yeah, there's nothing really to cancel because there isn't anything. So what happens here, we just relate with them. That's what you meant when you said cancel. I know that I'm just being pedagogical. Now, from your free body diagram, what do we then have for the net force, or in other words, your total force in the y direction?
W2 minus T2.
It has to be W2 minus T2. If we had T2 minus W2, what would we be saying the object's doing? It'd be moving up, which it is not. So this would be W2 minus T2 equals M2 A2Y. So we have this equation, and then we have this equation. Then we started doing a couple things here. So naively, you could say, well, wait, we have 4 unknowns. We don't know T1, we don't know A1X, we don't know T2, we don't know A2Y. It looks like 4 unknowns. But I tried to convince you on Friday there was only 2. So I'll start with the accelerations. Why is this acceleration here? Why is this acceleration here the same as this acceleration here? By a string. Right, so they're connected by a string. So if this one falls a certain distance, what does this one do? Moves the same distance, like that, they're connected. And if this falls at a certain time, this moves in the same time. So they're moving the same distance, same time, they have the same acceleration, so we just call it A. So we did on Friday. We said A1X equals A2Y equals A. Now, what did we say about T1 and then T2? We said if that string is massless, and if that pulley is massless, okay, and frictionless, what do we know about the tensions? They're the same. So we can say that T1 equals T2 equals T. So I'm going to rewrite these equations here. This one here is my T equals M1A. My other one is then going to be our W2. Okay. This W2 here, I'm going to write this W2 as M2G. As M2G minus T equals M2A. These are the equations. 2 equations, 2 unknowns. Does that make sense? Now what do we need to do? We need to solve these. So solve for A and T. Okay, so how would you solve these?
T from the first equation, rather than T in the second equation.
Yeah, you take this T. I'm going to give you 2 ways to do it. There's going to be one way that's actually going to be a lot easier to do, but let's do that here. In this case here, you're not going to see the power, but I'm going to show you. You won't really see till we look at another problem that has a little more F to it. Okay, so what I can do is solve. Use one of 2 methods. The first method. Sub one of the unknowns. So solve one equation for one unknown and sub into the other equation. So let's use that method. Okay. Hey, let's solve for T here. Done. There's nothing else to do. So in this case here, I have this guy here. And I'm going to substitute this into here. So I substitute that into here. Now, how do I solve that? Okay, I'm gonna get a lot of times things like this. I have an equation like this and somebody will then divide through by M2 and say, I'm done. I solved for A. Why do you not do that? Or if we're trying to solve this for A, how many A's do we have? One here and one here. What do we have to do with all the A's first? Get them on one side. I factor out the A. And then I divide through by that free factor. This tells me the acceleration is this. Why is that considered solved? Because when we do these problems, what do we always assume we know? We assume we know the masses. So I've written the acceleration in terms of things we know, and we know we're at or so or G is 9.8. So basically, the masses are known. So A can be calculated. Okay, so what you're going to do in the lab this afternoon, that's going to be the first thing you're going to test. What you're going to do is you're going to have a card here. We're going to have a string. The string is actually going to be tape like this. We're going to have tape. So you go over this pulley here like this. This is going to be our frictionless pulley. We have a little mass here like this. You're going to turn that on. That's going to fall. And using the sonic rangers, you can actually then determine the acceleration of the cart. And you're going to compare it to that equation. It's going to work actually really quite well. Questions with that? Now, let me show you another way to do this. Method 2. Okay, well, let's see how much people have been paying attention to it when you were in 9th grade or 8th grade. Okay, what's the other way to do this? That's the way we're going to do them because it's going to be the really lazy, slick way of doing things. Add the equations. Let's add the equations. Okay, so I'm going to take those equations here. And this equation here. I just add them. Hey, if I add them here, what do these do? Cancel. Boom, boom. So I get M2G equals M1A plus M2A. I call out my buddy A. We'll add through by this and I get the exact same result. When you get more involved equations, that's going to be the beauty of that approach will be very evident. Right now, it's kind of a simple equation. You look and go, eh. It'll become more apparent in a little bit. That makes sense. Now, how did you then get the acceleration? I mean, how did you then get the tension?
Acceleration would be good.
Yeah, I could take A and I could put it into either this equation or this equation. Okay, which one would I use? I could use use the first one, because why? There's no work involved. You just basically take your value, multiply it by M1 and you're done. This one I actually have to solve for the tension here. That makes sense? Questions? Okay, let me give you a little thought question here. If the objects were initially at rest, could we use x equals x naught plus vxt plus 1/2 at squared, v equals v naught plus at, v squared equals v naught squared plus 2a delta x to find v and x. What do you know about these equations here? Only true for constant acceleration. Do we have a constant acceleration in this problem? How do you know? That's correct. Because our acceleration depends only on constants. The masses are all constant. G is a constant. This is a constant. The fact that this is a constant means that I can now use these equations. So what have we done? We've coupled basically the new stuff all to the old stuff. And that's what's going to happen in this class, is that nothing gets thrown away in this class. Everything gets coupled together. This is going to be one big, long logical argument that we're doing. That makes sense? Let's try one that's a little more involved. And it'll be the other thing you're going to do today in lab. So here we have an inclined plane. It's going to be frictionless right now. We're going to relax that condition in a bit. Here's a mass here, M1. Here's our massless frictionless pulley, and here's our mass here, M2. Okay. Which way do you want the system to move? Do you want the system to move this way or move this way? I don't care. I'm going to go with the first one here. Up the ramp or down the ramp?
Down.
Down. Okay, so the system's going to move this way. Why? Because Carter said down. Is that what you meant by down? Or did you mean the massing?
That was good.
Okay. So we're going to do that. Okay. I want to find A and T for the system. Okay, you tell me how to proceed.
Draw your body diagram.
Draw a free body. Now, why would you know to do that? That's correct. Okay, let me give you the dumb answer to this. The dumb answer is it's almost always right. And it certainly may not always help you, but it's never wrong to do that. That's kind of the brain dead answer. Now, why does that wording of that problem tell you you probably want a free body diagram? What are we finding? Acceleration and they were connected with forces. That's why we moved that. Okay. So here's my buddy M1. What are all the forces acting on my buddy M1? Going straight down. Okay, what do you think the most tempting answer is for the weight? Yeah, something going like this into that block. And again, weight can only go down. Keep going. Going how?
Perpendicular to the surface.
Yeah, that normal is no longer going to be like that. It's going to be perpendicular to that surface. Here's my surface, and so perpendicular is that way. So this right here, I'll call this M1.
And then mention
Going.
diagonal.
It's always going to go along the string, and so it's basically going to go like this. Tension. Now, what's going to be our coordinate system for this? How do we always draw our coordinate system? To always basically reflect how the system is moving. It's going to have that same symmetry of motion. So how's M1 move? Down here like that. So I'm going to take basically a skewed coordinate system. I'm going to take a coordinate system that looks like this. What that means here is that this is really my y-axis here. That's my y-axis. And this right here, that's really my x-axis. And which way do you always take it to be positive? The way the object moves. So which way is positive in this? Well, going down the inclined plane. Okay. Now, let's go on to the next one, and then we'll come back and tinker with this. Okay, so here's my buddy M2. What are all the forces on my buddy M2?
Mass or weight W2.
Okay, so this would be my W2
And then tension.
going up. Why didn't I use T1 and T2?
Because it's the same tension.
They're the same tension. Okay. Now, what's my coordinate system?
Just a normal.
Yeah, it's just going up. So we're just going to take a normal thing. And which way is positive then?
Up.
It's going to be up on this one here. So let's start out applying F equals MA. Let's do F equals MA on this one first. Then we'll go over this one. To this one, because we're going to have to do something a little bit more on this one. So here's our F net. Equals M2 A2. Hey, what do we do with that? Break into components. Guess I should have had my X's set first. What am I going to do with X? How come? Because there's no forces in the X direction. So let's ignore this. Okay, from that free body diagram and the coordinate system, what has to be your net force, or in other words, the total of your forces?
Minus W2.
Why isn't it the M2G minus T?
Coordinate system.
Yeah, which way is positive here? Going up is positive. Okay, so we're going to have the tension minus this. If this are falling down, then what would we have? M2G minus T. So this one here is going to be T minus M2G equals M2A. Now, why am I suppressing the 2 here and the Y here?
Equal.
Put in more details, so put in more nouns.
A2Y equals E1X.
Yeah, the acceleration of object M2 is going to equal the acceleration of object M1. That's why I'm going to suppress. I don't have to include those. Does that make sense? So here's my one equation. How many unknowns there? 2. Tension and acceleration. Okay, now what do we have to do next?
Make their equation.
Yeah, let's go over here and apply the equations on this side over here. So let's apply F equals MA on this. Pick this up in X and Y components. Okay. Well, this one's a little more tricky. What are all the forces from this free body diagram and this coordinate system here? What are all my X forces? Is tension an X force? Yeah. Here's my new X axis here. So tension's an X force. That works. How about my normal?
One.
Yeah, so the normal is going to be a Y force. It's not an X force. What about the weight? It's going to be both. So what am I going to have to do to my buddy, the weight? I'm going to have to break it into components. Hey, how do you break a vector into components? Draw the picture first. More.
Okay.
I'm going to go here to the tip of that vector and do what?
Drop your perpendicular to one axis.
I'm not going to, don't even draw this. Don't go like this and say, oh, here's my X component and here's my Y component. Why is that fundamentally flawed? What do components always have to be?
Perpendicular.
Mutually perpendicular to each other. So So how do we do this? I go here and draw my perpendicular to this one here, like that. That's perpendicular. So then this one here, I'll put an arrow here. So this is my WY. And that one here, that's my WX. Now the question is, okay, so let's write this out and then we'll kind of take with this. So if I come over here, what then are my forces in the X direction? My net force in the X direction, from that free-body diagram. Which way is positive? Going down. Why? Because Carter said it's going down. So what do we have? Again, the net just means the total or the sum of the forces in the X direction.
M1G sine theta minus T.
Okay, I'm going to call this WX, but what you said is correct. Okay, it's going to be this WX component minus the tension. Equals M1, and I'm going to call this A. What do I have for the net force in the Y direction? Where are all my Y forces? Is it moving up or down on the inclined plane this way? Okay, so which way do we take to be positive? It doesn't matter. Pick a direction. I'll go with the first one here. Up or down? Okay, up was positive Y because I heard Molly sit out. Okay, so from that, what are your forces in the Y direction?
M1 minus W.
It has to be this N1 minus WY. So this has to be N1 minus WY equals M1. And what is the acceleration of the Y direction for that object? It isn't, right? It's not moving in the Y direction. So this has to be 0. So what does this tell you? It just tells you that the force going up has to equal that force going down. Right now, that doesn't help us. So well, when we put in friction, but we're not quite there yet. Okay, now the question is, we need WX. And I was forced to erase the picture here like that. So here's our picture like this. Here's our M1, here's our M1G. Okay, here's your WY, here's your WX, and this is theta. The question is, where is theta in that triangle? So this theta here is where here? We have two choices. It's either here or it's here. It can't be here because that's 90. So here or here. It's only the top one here. That's going to be my theta. So let's go through and do the argument for it. So okay, this is where the geometry course you have in high school, which has now been destroyed. At one time, geometry in this state was actually beautiful because it was actually part of what you learn in geometry is actually logic. That's really almost the important part of it. It's actually how do you construct a proof is actually an argument in logic. And now it's basically been converted to let's find the volume of really stupid objects. And somehow that's geometry. It's been utterly destroyed in this state. I'll get off my soapbox now. So convince me that this angle here has to be theta. Okay, we have theta here, we have an angle here 90, and I'm going to call this here angle here alpha. What do I know about theta, 90, and alpha?
Yeah.
They have to add up to be 180. If this is alpha here, where else do I have alpha? Right here. This also has this angle right here. It's kind of small, sorry about that. That's also alpha, and here's 90. So that angle here must be theta. Okay, pretty slight. Okay, so what is this going to be then? This hypotenuse here is M1G, right? This is my M1G. And this side here has to be then. And this is theta. What part of the triangle is this?
Opposite
The opposite. So I have to use
side.
sine. So this WX is going to be M1G Sign up there. So if we put this all together, what do we get? We get M1G sine of theta minus T equals M1A. Does that make sense? Questions? Okay, so now all the physics is now done. Now we just have to solve. So how am I going to solve these? First of all, what are my unknowns again?
T,
The tension and the acceleration. So how do I solve these? Add them. Okay. So I could solve this equation here for T. Put this in here and then crank through the math. Perfectly acceptable. It's going to be easier just to add them. So I'm going to rewrite both the equations and then just add them. So I'll start with this guy over here. So I have T minus M2G equals M2A. And then my buddy over here, M1G sine of theta minus T equals M1A. I'm going to add these. What wonderful thing happens when I add them?
T cancels.
That T cancels the minus T there. And what do I get? I get this fellow, M1G sine of theta. Minus this one comes into the minus sign. Equals what? My M1A plus M2A. I'll factor out the A here. And divide them by that free factor, and I am done. My acceleration is M1G sine of theta minus M2G all over M1 plus M2. And that's going to be your second part of the lab. In the second part of the lab, what you're going to do, you have the exact same setup. But you're going to take a block. You're going to take a block, you're going to put it up here, like that, and that's going to be your setup here. And then you're going to let this fall, or it might even go the other way, it won't really matter. And you're going to basically get the acceleration, and you're going to compare it to this equation. That makes sense? Questions? Okay. Let's try another one. So this is theta, this is still going to be frictionless. M1 here, pulley, M2 here, pulley, M3 here. Which way do you want that system to move? Like this or like that? I don't care. Now let's do this way because we did down. Now we go this way. System's moving like that. Why? Because I made an executive decision. Okay, what are we going to find in this case? Find the acceleration of all the objects and the tensions in the rope. So find the acceleration of each mass and the tensions and the string. Okay, you tell me exactly how we're going to do this. How many? We're going to have now 3 free-body diagrams. So we have M1. What are all the forces on my buddy M1?
It's weight.
Going straight down. Do not make it go at an angle. M1G.
Normal, good service.
Good. So we're gonna have the tension, that string going this way. What's our coordinate system? How's it gonna look? It's gonna be skewed because always take your coordinate system to have the same symmetry as the object moving. Since this is going up like that, I'm gonna take a coordinate system like this. So that means that this right here, this is my x-axis. And this right here is my y-axis. Which way will be positive for M1? Yeah, it's moving up the incline, so we take that to be positive. Okay, we'll come back to that. Okay, tell me about my friend M2.
Weight going,
What?
weight going down.
Rate going down. Normal going up.
Tension on both sides.
Tension on both sides. Okay, and what's the coordinate system? It's just going horizontally like that, so it's going to be just a standard thing. And which way do we take to be positive? It's going like that. Now, there's a technical problem here. What's the technical problem? Yeah, if I leave it like this, if this t equals t here like this, what can that object not do in the x direction? Well, it can move, but it can't accelerate. Okay, so in other words, this thing here could fall, but it's going to have to fall at a constant velocity, and that need not be the case. So how can I fix this? When did we say the tension is the same? In a string that's massless, and the pulley's massless as well. So that means that all this tension here is the same. All this tension over here is the same. And all this tension is the same, but this tension here does not have to equal this tension here. So how do we fix it? We just use different notations here. So I could use left or right or 1 and 2. Which one do you want me to use? 1 and 2. So I'll call this T1. I'll call this T2. What do I then have to do to this one over here then? Yeah, all this tension on this side here. This is all going to have to be the same tension, so I have to put a T1 there. Does that make sense? Okay, now let's do my last friend. Friend M3. Is M3 still on the board? Yes, M3 is still on the recording. Okay, so what are all my forces? That looks like a sad M3. That's a little better. Okay, so what are all the forces acting on my buddy M3? Tension. Talking about that tension. It has to be T2. Because all the tension on this side is the same. So I'm calling this one T2, so this has to be T2. And what's my coordinate system? Like our standard little normal thing. And which way is positive on that? Yep, this is moving down. So we call that to be positive. And does that make sense how I set up all those true body diagrams? If there was a fourth mass, you'd just keep on doing this. There's no variation on any of these. Now, let's go through and do this. What's the next step with these? F naught equals MA. So I'm going to have my F naught here equals M3A3. I'll have my X equation here. Hey, what am I going to do with my X equation? Ignore it because there are no X forces. Okay, now I look at my Y force here, which I'm going to go up here like that because I'm running out of, I'm actually going to go like this because I'm running out of room. I'll say F naught Y equals M3A3Y. What are all my forces in the Y direction on this object? With this coordinate system here?
M3G minus 2T.
Why is it T2 minus M3G? Down is positive. So it has to be this, my buddy here, minus T2 equals M3A. Now, why did I call it A3Y? What am I going to know about all the acceleration of each of these masses here? They're all going to be, because, yeah, they're all being connected together. So if one of them moves a certain distance, they all move that same distance in the same time. All the accelerations are the same. So one equation. Okay, now let's go over here. F net equals M2 A2. I'm just going to look at the X equation here because I want to finish this before the class ends. What are all the forces in the X direction on my friend over here?
T1.
Okay, so how do I write it?
T2 minus T1 minus T.
Yeah, it's going this way is positive, so it's this tension minus this tension. Equals M2A. Okay. Now, come over here to my buddy here. Say my net force was M1A1. Look at that, the X force. And what are all my X forces here? Tension and, okay, part of the weight. So what do I have to do with my weight here? I have to find the components. And tell me how to find the components? To this y-axis. So I'm going to drop my little perpendicular here. So this right here, that's my WY. That's perpendicular. And this part right here is my WX. My angle theta is here. So you tell me what to put in for the net force in the X direction.
Sorry, yes, sine of theta minus T1.
Okay. Which way is positive here? Moving up like this. So what do we have? Is the T1 positive or negative? It's going to be a positive force. So I'm going to have T1 minus, and this X component here is going down this way, so it's a negative component. Minus WX equals M1A. And my WX here is going to have to be what? If my hypotenuse is M1G, if this is theta, my WX has to be
M1G sine.
M1G sine of theta. So this has to be T1 minus M1G sine of theta equals M1A. So how many unknowns do I have here? In all of them in this problem?
3,
T1,
T2.
T2, the acceleration. How can I solve these now? Add them. So let's do that. I'm going to go about a minute long, but I want you to see this. So I'm just going to rewrite all the expressions here. It doesn't matter the order. My buddy over here. I add them. And if you've set up everything fine, what should happen to the tensions?
Cancel.
They better cancel. Okay. So here's a T1, a positive T1, here's a minus T1, they cancel. Here's a positive T2, here's a negative T2, they cancel. So you're done. I have my friend here. Then I have minus my friend here. What do I have on the right sides? This and this and this. I have M1A, M2A, plus M3A. What do I do on that right side? You pull out that A. I will divide through, and then this will be the same slide. Divide through by this prefactor, and Shazam, I have myself an acceleration. This is M3G. minus M1G sine of theta. All of M1 sum 2 plus sum 3. Boom. It doesn't matter how involved the system gets, this method will work for absolutely every single one of them. Okay, that's beautiful. Okay, have a great day. See you in lab this afternoon.